This Zoom session is being brought to you by the Fractal Hex Horizon. All right. Yeah, we ran off the edge of the book, didn't we? Here we are at 5-7, and I've already opened up the final. So you may hand in all that stuff at your leisure. We have at least a month to go. So in these last few days, last couple weeks, I guess I'll be essentially doing office hours. However, I would like to cover materials in this extra amongst this extra credits set. So, for example, um, well, golly, let's try. Which will it be? Inverse trig. Now let's start from the beginning to the end. Here we go. Hourly trig. Hourly trig. This is that's a name I made up. And I define an hour as 1/24th of a circle, which you would divide 360 degrees by 24. That's 15 degrees. And I call an angle hourly if it's an integer multiple of 15 degrees. 0, 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, and 180. And I call a triangle hourly if all of its angles are hourly, multiples of 15 degrees. Here are the right angle hourly triangles: 45, 45, 90, and 60, 30, 90, and 75, 50, 90. Now, these are considered classic triangles. The 45, 45, 90 is sides 1, 1, and root 2. And you can get these trig functions from that diagram. And the 30, 60, 90 triangle has sides 1, root 3, and 2. Okay, fine. Now, here's one. 15, 75, 90. What are the proportions of its sides? Okay, well, here we go. Now, actually, we can find trig functions of 50 and 75 degrees by using angle subtraction and addition formulas on 30, 60, and 45 degrees. Also, you can derive it oneself from any of a number of what I call right hourly dissections of right hourly triangles. Let's, for instance, take take this one, the 45 degree right triangle, and break it into here's a 30, 60, 90 triangle, here's a 45, 45, 90 triangle, and in here is a 15, 75, 90 triangle. Start with this side here. Give it a length of 4. All right, now this is a 30, 60, 90 triangle here. So this side is half of 4, which is 2. And this side is root 3 times that, so it's 2 root 3. Now this is a 45, 45 triangle. So if this side is 2 root 3, then so is this, 2 root 3. And this long side is 2 root 3, and this side here is 2. And this part here is 2 root 3 minus 2 in length. Now this is a 45, 45, 90 triangle, and this is the long side, and its short sides are this divided by the square root of 2. So 2 root 3 minus 2, if you do the math, it comes out to root 6 minus root 2 here and here. And finally, this long side here is it's in a 45, 45 triangle. This side here is 2 root 3, this side here is 2 root 3, this side here is root 2 times 2 root 3, which comes out to 2 root 6. So this long side here is 2 root 6. This part of it is root 6 minus root 2. So this part here is 2 root 6 minus root 6 minus root 2, which comes out to root 6 plus root 2. So now we have a triangle 4 on the diagonal. Root 6 minus root 2, short side opposite the 15 degrees. Root 6 plus root 2, medium size opposite the 75 degrees. And now we have the proportions of such a triangle. 4, root 6 minus root 2, root 6 plus root 2. If we did the same thing here, here's a 30, 60, 90 triangle. We take out another 30, 60, 90 and take another 45, 45, 90. And here also is a 15, 75, 90 triangle. And if you work it out and you make this side 4 here, then going by a process of elimination through the whole sides, we again with the same proportions: 4, root 6 minus root 2, root 6 plus root 2. In an earlier problem set, which I think is still available in the problem sets, whoops, is I did this triangle here. And again, it's the same deal. Start with this, with a 45, 45, 90 triangle. Here's a 30, 60, 90 triangle, a 45, 45, 90 triangle, and a 15, 75, 90 triangle here. And we give this length 4, then going through the same process of elimination, get this is root 6 minus root 2, this is root 6 plus root 2. So here we have these right hourly triangles have these proportions. The isosceles, the 45, 45 right triangle has sides 1, 1, and root 2. The 30, 60, 90 triangle has sides 1, root 3, and 2. And the 15, 75, 90 triangle has sides root 6 minus root 2, root 6 plus root 2, and 4. Now from that, we can derive the cosine, sine, and tangent of each of those triangles, each of those angles, 30, 45, 60. These should look familiar. Root 3 over 2, a half, root 3 over 3, root 2 over 2, root 2 over 2, and 1, a half, root 3 over 2, and root 3. Now, for cosine and sine, let's say 15 degrees, cosine is adjacent over hypotenuse, therefore root 6 plus root 2 over 4. Sine of 15 degrees is opposite over hypotenuse, therefore root 6 minus root 2 over 4. Reverse for 75 degrees, its cosine is root 6 minus root 2 over 4. Its sine is root 6 plus root 2 over 4. As usual, complementary angles have complementary trig functions. And then tangent, right? For both sine over cosine, if you divide this by this and do some reduction of rationalizations of denominators, it comes out to 2 minus root 3 for the tangent of 15 degrees. If you do this over this, root 6 plus root 2 over 4 divided by root 6 minus root 2 over 4, and cancel the 4s and rationalize the denominator, you get 2 plus root 3 for the tangent of 75 degrees. It's also, you can find sine and cosine of 15 degrees by the half angle formula and get this, I consider, rather more gnarly formula. I don't really like it that much because it is a square root and a square root. Same for cosine. And again, I don't really like these that much. These happen to equal, like I say, these values here. And I personally prefer these. I believe that the hourly triangle, 15, 37, 45, 70, 60, and 75. And those are the only triangles whose sines and cosines can be written without square roots inside square roots. Here. I believe that's the case, because if you could, then you can use angle addition and subtraction to get even more even finer division of the circle. I may be wrong, but I believe that's the case. So here we have these right hourly triangles. And let's see. I'm sorry this is all sideways, but here I have a complete right hourly diagram. Draw this, and with all these sides on it, and get all these different triangles in it of different different angles, and all these different sides. I'll leave that for you to look up. Here I talk about all the hourly triangles. There are only so many triangles, only a finite number of triangles whose angles are all multiples of 15 degrees. 15, 50, 150, 15, 30, 135, 15, 45, 120, 15, 60, 105, 15, 75, 90, 30, 30, 120, 30, 45, 105, 30, 60, 90, 30, 75, 75, 45, 45, 90, 45, 60, 75, and 60, 60, 60. Okay. And you can find all these triangles inside this diagram for what that's worth. And so from there, let me see if I have this right. Right. Page 6 of this problem set, I go over the law of sines, which we've gone over before. A over sine alpha equals B over sine beta equals C over sine gamma. So, and then from there we can get values for A and B given C, alpha, and gamma. And from that, we can get a formula. Here we have the area of a triangle with one side C at angles alpha and beta. And you work it out. This is an angle side angle equation for the area of a triangle. Number 6. All right. From that then, these pages 7, 8, 9, 10, 11, and 12, I ask you to solve basically all of the hourly triangles. The exact area values of A and B in the area. In reduced radical form, I request that, no square roots in the denominator, of the sides in the area. Here's a 15, 50, 150 degree triangle with along side 1. What are A and B? Well, okay, it's obvious they're equal, but they're both equal to what? Here I put this side here be 1, this shortest side here be, so 1 here and A and B here. Again, what are A, B in the area? Here we have a 30, 15, 135 degrees with a long side 1. What are A and B? We have the 30, 15, 135 with this middle side equal to 1. Here, the same triangle with this side, the shortest side equal to 1. And in each case, what's A, what's B, and what's the area? And again, I ask for exact radical form. Decimal approximations are not what I'm asking for here. And again, I don't want square roots in the denominator. So you'd have to do some of that tedious radical reduction work along the way. That's for 7. 8, let's see what we have for 8. Pretty much the same thing. Here, the triangles are 45, 50, 120. Here and here and here with 1 on the long side, on the middle side, and on the short side. What's A, B in the area? Here we have 60, 15, 105 degrees. 1 on the long side, on the middle side, and on the short side. What's A, B in area? Here, 75, 50, 90. Okay. Again, A, B in area. And we shift 1 around all 3 possibilities. 30, 30, 120 with 1 along the long side and 1 along one of these 2 equal sides. I mean, obviously in this case, since 30 and 30 are equal, A has to equal 1 in this case. But what's B and what's the area? All right, 45, 30, 105, here, here, and here. 30, 60, 90, 1 here, here, and here. 45, 45, 90, okay, here and here. And again, in this case, obviously, since A has to equal 1 and this 1 are equal, since this is isosceles, is a 30, 75, 75, and 30, 1 here and 1 here. Oops, how did that happen? Oh, I'm sorry, what did I just do? Wrong. And here, chapter 12, it contains the isosceles triangle, A, 60, 60, 60. So obviously A and B equal 1, that's obvious. But what's the area? Not true, not quite as obvious. And it also contains the 3 versions of my absolute favorite triangle, 60, 45, 75, because it contains an angle from each of the classes. 60 is 30, 60, 90, 45 is 45, 45, 90, 75 is from the 75, 15, 90. And it has a kind of a tilted quality. I nicknamed this triangle the jaunty triangle, like because you're wearing a beret at a tilt. And again, put 1 here or here or here, and in each case, what's A, what's B, and what's the area. And again, in reduced radical form. So I offer this to you as an extra credit set. 30 points, that's nothing to sneeze at. And and I particularly like it because basically by doing this problem set, you will have completely solved an entire area of mathematics because these are all the hourly triangles, which is, I kind of feel I somehow obligated to show you at least some part of math which can be finitely and completely mastered. I must admit that I felt a great deal of satisfaction when I mastered these triangles myself. Okay, well, that's hourly trig, and maybe I'll review it in a later class if other people show up. There's hourly trig, and here's a trig table for an hourly trig table. So degrees, so 115 to 345 degrees. What is the angle in radians? What's the sine? What's the cosine? What's the tangent for each of these angles? And again, that's a finite bit of math which can be solved completely. And it's worth up to, how many points did I give here? 24 points in all, 1 point per row. I think you can't get a better deal than that. So I recommend working on it. And okay, there's a section, well, later I'll talk about, maybe a later class, I'll talk about Pythagorean triple. This is a way of remembering trigonometric identities. I saw it online there. It was called a super hexagon. Okay, that's cool. Here we go. And so we draw this sine, cosine, tangent, cotangent, secant, cosecant, and 1. When they're opposite, tan and cotangents, cosine and secant, sine and cosecant, they're reciprocals. So these examples. If it's this, this, and this, then A is B, then A times C equals B. Sine times cosine. Tangent is cosine. Tangent times cosine is sine. Sine times secant is tangent. Cosecant times tangent is secant. Cotangent times secant is cosecant. Cosine times cosecant is cotangent. So this is a simple way of keeping in mind various trig identities. And super hexagon 2, same diagram. Now, if you flip through a diagonal around an axis, then you get co-functions, sine and cosine, tangent and cotangent, secant and cosecant. Oh, and there's also, if you spin around here and here and here, sine squared plus cos squared is 1 squared. Cotangent squared plus 1 squared plus cotangent squared is cosecant squared. Tan squared plus 1 squared is secant squared. Okay, never mind. So again, this is a cute little way of remembering various formulas. These two I'll go over later. It talks about a particular trig problem I call antenna on the roof. This is some relations between cosines and sines. Here's a set of problem sets about inverse trig functions. Here, this does what I call stereo vision. It's a trig problem involving stereo vision. This talks about the height of a tree. These pendulum problems are all about side-side angle problems, and it gives various formulas. And this involves a special function I call tangential addition, where it's equal to the the tangent of the sum of arctangents. I'll discuss that in later classes. So this is if you wish, I recommend going through this as a way of getting ahead on whatever problems, get ahead of getting extra credit points and thereby making up for whatever problems you have with your other problem sets. Well, all right, like I say, we're off the edge of the class, so I'd say these are office hours. So do you have questions, comments, suggestions, requests, specifically about problems and the homework or the finals or the quizzes? All right, then. Not. Then, motion to adjourn. Is it seconded?
Aye.
It is seconded. All right. Well, I'll be here. Mondays and Wednesdays until the end of the semester, and essentially giving out office hours. Again, if you have questions, please show up and talk to me. All right.
Thank you.
All right. You're welcome.
Thanks, Professor.
You're welcome. I'll be seeing you later. Swallow wrong.